in any dimension, we'd say that the divergence comes from modes localized near the boundary. And therefore, we'd learn in any dimension that the leading divergence is proportional to the area. But our calculation today will be in two dimensions where things are a little bit easier. The area is independent of L, and therefore we expect the divergent part to be constant. So we expect, therefore, two facts. One, we expect that the entropy is a function only of the ratio L over epsilon. Secondly, we expect the divergent part that we can pick out by taking epsilon d by the epsilon is independent of L. So we expect these two properties of the entropy. And putting them together, we see that we expect the entropy to be a constant times the log of L over epsilon. A constant times the logarithm is the most general function of L over epsilon that only depends on L over epsilon and has the property that its derivative with respect to epsilon doesn't depend on L. In other words, the log is a function only of the ratio, but it's also a difference of a function of one variable and a function of the other. And it's the unique function of the ratio that is such a difference. So we're expecting this behavior, and that's the behavior that we'll find after a small analysis. Now, most calculations of entropy in quantum field theory use the replica trick. So what is the replica trick? Well, the replica trick is simply the following formula, that you look at the trace of rho to the n, and you differentiate it with respect to n, and take the limit as n goes to 1. And that is equal to S of rho. Because if you take this derivative and limit, you'll find that the right-hand side is minus the trace of rho log rho. So as we'll see, trace rho to the n is much easier to calculate for integer n, positive integer n. And then we analytically continue from there. This replica trick was actually introduced first, I believe, by Edwards and Anderson in studying spin glasses, disordered systems. It's extremely useful there and also here. Since we're analytically continuing just from integers, you might want to ask what we're doing. In ordinary quantum mechanics, the replica trick is actually correct in the following sense. The trace of rho to the n is holomorphic and bounded in ordinary quantum mechanics for the half-plane real part of n equal to or bigger than 1. And by a theorem known as Levinson's theorem, such a function is uniquely determined by its values at integers, at natural numbers, positive integers. You can't arbitrarily specify the values at positive integers. There generically won't be such a function. But if you know that, well, If the function exists, of course, the values at the integers exist. If you're given the values at integers, and there is an analytic continuation to a function holomorphic in the half plane and bounded, then that analytic continuation is unique. So in ordinary quantum mechanics, it's true that you could reconstruct the entropy from the values of trace rho to the n at integers. In ordinary quantum mechanics, although true, it's not normally a useful procedure. In quantum field theory, first of all, it's not really rigorous because we don't, well, we'll see that the notion of the density matrix really has some limitations in ordinary quantum field theory, so that we're not really in the setup where you could make this argument rigorously. On the other hand, it's true in ordinary quantum field theory, as you'll see, that computing at integer values is much easier than computing at non-integer values. And what happens in practice is very frequently that when you compute at integer values, there is a simple analytic continuation that satisfies the conditions of Levinson's theorem and strongly suggests that that should give the correct value of the entropy. And in practice, this is found to give extremely good results. Well, to compute rho to the n, any questions before I go farther? Well, okay, to compute the trace of rho to the n, we need a reasonable description. We need a useful description, not just a description. Of rho. And we can get that as follows. Sorry. There's something basic that no one asked me. I didn't state it properly. I said we're going to calculate the entropy of the density matrix, but I didn't say which state the density matrix would be for. So we're going to compute for the vacuum. For the interval I, or equivalently for its domain of dependence. But the UV divergence we find will be universal. That's because any state can be approximated by the vacuum at short distances. So in any other state, some modes are excited relative to the vacuum, but most are not. And the ultraviolet divergence comes from modes of arbitrarily high energy, which are almost all unexcited. So while we compute for the vacuum, we'll get a universal. Because we get an ultraviolet divergence, it will automatically be universal and valid for all states. But since we're going to compute for the density matrix of the vacuum, we need a useful description of the density matrix of the vacuum. So the first step, we need a useful way to describe the vacuum. The vacuum or ground state. Well, what we know from our study of field theory, hopefully, is that such a representation comes from Euclidean path integrals. So we consider, here's a time zero surface on which we want to define the state psi. What we hopefully know from our study of path integrals in field theory is that a Euclidean path integral on the half plane where T is negative, computes the ground state psi. What it means, for example, in a scalar field theory, what is meant by a wave function? In a scalar field theory, for example, the wave function is a functional of 5x, where x is in the time zero surface, where we're trying to define the state. So what Feynman would tell us is that if you specify boundary that phi equals 5x at time zero, and do a path integral on the Euclidean past with that boundary condition at time zero, the output of the path integral with that boundary value will be a function psi of 5x, which will be the ground state wave function. So hopefully you're familiar with that from your prior study of field theory. Now, if we know that that's true, then we can easily construct the pure state density matrix for psi on all of time zero slice. Namely, as I just said, we use a path integral on the lower half plane to compute the ket psi, but likewise, a path integral on the upper half plane will compute the bra. Now, in this picture, the two black lines are both represent time zero. I've just drawn two copies of time zero because the bra and the ket are both functions of psi of x. Let's say one is a function of psi of x prime, and the other is a function of phi of x, where x lives here and x prime lives here. So to compute the pure state density matrix, we do a path integral in the lower half plane with boundary values phi of x, and a path integral in the upper half plane with some other boundary values phi of x prime. And the product of the two is a density matrix that depends on both sets of variables. And of course, it doesn't contain any information that the ground state wave function itself did not contain. All we've done is to do the same computation twice, calling one the ket and one the bra. Well, why have we done this? What we want to do, so this is rho for the whole t equals 0 plane. We want not rho for the whole t equals 0 hypersurface, but rho for an interval I, where okay. Let's say this is the interval I, and we want to integrate out, to use the jargon, the fields elsewhere. So we want to remove, this rho is analogous. Okay. We want to construct a density matrix just for fields in the region I, not for the fields outside. So to construct a reduced density matrix, for the fields outside of I. Sorry. We want to construct a reduced density matrix for the fields in I. We trace out the fields outside of I. What does it mean to trace them out? What it means is that we sum over the unobserved. If you imagine we're making observations only in the region I, we think of the regions outside of I, or a space like separated from I, as unobserved regions. We sum over all the unobserved values of the fields outside of region I. Now, summing over those, tracing them out, means setting them equal in the bra and the ket. So we set phi of x equals phi of x prime outside of I with no constraints within I. So it's easy to explain how to do that in a picture. So the picture we have so far was this one. And let's say that I is this bit. So we want to set the fields, we want to trace out the degrees of freedom outside of I, which means setting the values equal in the bra and the ket. So that means we have to glue together these portions while doing nothing in region I. So if we glue together means setting phi of x equal phi of x prime. The reason that I drew separately 2 copies of the time zero surface is that we were allowing different boundary values coming from above or coming from below. But to construct a density matrix only in region I, we want to allow separate values in the bra and ket only in region I, not in the region outside region I. So if I glue together the regions outside of region I, I'll get a picture that will look more like this one. Only region I will be doubled. And since I glue, then outside of region I glue everything together. And now the picture looks just like this one. We have R2, which we can also think of as the complex plane. With a cut along I. So somebody has literally taken scissors and made a cut in the plane along I. And now to calculate rho of phi of x prime, phi of x, which is now the density matrix for region I, we do a path integral on the cut plane with the boundary values phi of x below and phi of x prime above, and no other condition. Someone asked in the chat if I should elaborate on what I mean by scale invariance. Scale invariance means rescaling all lengths by a common factor. It's a special case of conformal invariance. The way I used scale invariance means that something dimensionless like the entropy can only depend on dimensionless ratios. And in this problem, there only was one dimensionless ratio, L over epsilon. L is the length and epsilon is the ultraviolet cutoff. Now, before I go on, any more questions about this description of the density matrix? Because if that isn't clear, the rest of the derivation will really be mystifying. You cannot unmute yourselves. I thought you could unmute yourselves. Let's let people unmute themselves. At my end, it says you can unmute yourself.
Professor Witten, I was wondering whether you could add any commentary on the role of spatial boundary conditions.
What do you mean by spatial boundary conditions? Do you mean boundary conditions at the ends of the interval?
Yeah, sorry, I just couldn't unmute myself. Yes, at the entangling surface.
So you're actually, well, you're asking a question that has no good answer. It's related to the question is, you see, I said that there are two values, 5x and 5x prime. But at the ends, where we want to glue together those 2 points, that's very unnatural. So you might think you want to set 5x equal to 5x prime at the end. But the real answer is that there's no rigorous way. Well, in the...
I have to admit, it's a bit of a leading question.
Well, I'm not sure in which direction you think you're leading me. To me, the only direction your question leads is to say again that density matrix isn't a rigorous notion in quantum field theory, and we're going to discover its limitations as well as its usefulness. I'm not sure.
Yeah, it's a point that I've been confused about.
So you've asked a question that doesn't have a satisfactory answer, and that's related to the fact that density matrices are not rigorous in quantum field theory.
Okay.
Notice that in a lattice theory, your question wouldn't have arisen. In a lattice scalar field theory, some lattice points are in the region I, and there'd be no reason to set phi equals phi prime at the endpoints. So I think if we were in a lattice theory, you wouldn't have asked your question. And in a lattice theory, the notions we're using would have been rigorous.
Sorry, just
go
ahead. I just wanted to ask, so in this case, we're considering a unique ground state, right? The discussion would still be the same if the ground state was degenerate, or no?
Well, the discussion would apply for any ground state. So
for any ground state individually, okay.
Yes. You see, you would pick grounds. When I said you do the path integral in the lower half plane, I didn't worry about a boundary condition at infinity. If there's more than one ground state, you could select one by picking a suitable asymptotic condition at infinity.
Okay.
And whatever the condition was, everything I said would apply after doing that.
Okay, thanks.
Sure. Any other questions? Okay, I hope this explanation's been clear, because this representation of the density matrix of a region, well, I've presented it in 2 dimensions, but this part could have been equally in any dimension. We've simply explained how to formally use path integrals to define the density matrix of any region in quantum field theory in general. And assuming there's time, before the end of the lecture, we'll discuss Rindler space, where we will be in any dimension, and we'll use the same idea. It's only when we do a more detailed calculation that we're going to specialize to 2 dimensions. So we want to calculate trace row to the n. Well, let's start with trace row squared. That will illustrate the idea. So trace row squared, we need to have two copies of row. Then we multiply them and take a trace. So first, let's start with two copies of row. So I told you how to make one copy of row. You take the plane and you cut it on the interval I, and you do a path integral outside with specified boundary values. And the boundary values we called 5x below and 5x prime above. But for a second one, we'll call them 5x tilde and 5x tilde prime. So now the path integral gives us row of 5x prime. That's this one. And the other one gives us row of 5x tilde prime. Well, how would we multiply the two density matrices to get row squared? Well, if I have a matrix Mij and another matrix Ni prime J prime, to multiply them, I said J equals J prime and I sum. So in general, multiplying two matrices or operators means you set the second index of the first equal to the first index of the second and sum. So here, that means that setting the value, we have to set the values here equal to the values here. Now, geometrically, you do that by gluing. Gosh, I think it's possible somehow to get other colors. I wish I had some more colors. Okay. I can't quickly enough remember how to find another color, but we want to glue from here to here. If we glue this upper boundary to this lower boundary, that'll be the quantum field theory analog of setting the second index of m equal to the first index of n and summing. So gluing them together means constraining 5x prime to equal 5x tilde. And summing means we then just do a path integral over phi, over that value. So it's hard for me to draw it, but if you just glue this boundary to this boundary, locally you just make a smooth two-dimensional surface. An ant crawling down from above would reach this boundary and continue down here. So there's summing over phi after the gluing just means there's nothing special about that line anymore. That has been glued onto this. So the ant coming down from above continues down below. Now, after that, we have to take the trace. To get the trace of Mn, we then set I equals J prime and sum. So in the quantum field theory problem, we set this equal to this to multiply the two copies of row. And then to take the trace, we set this one equal to this one. So geometrically, that's accomplished by another gluing, which again, I have a little trouble drawing, but now we start here and glue it to the upper boundary there. So on one sheet above the cut is glued to the other sheet below the cut, and on the first sheet below the cut is glued to the second sheet above the cut. So what we've produced a two-sheeted cover of R2 branched at the endpoints of the interval I. There are two sheets which are distinct away from these endpoints. They are indistinguishable at the endpoints. If you go around the cut, you end on the second sheet. Because well, when you cross the cut, you go from one. If you try going around here, when you'll continue down below and then finish going around. Okay. I hope you can see from the picture that when we find the path integral that represents trace rho squared, we've constructed a two-sheeted cover. So the trace of rho squared is equal to a path integral on the two-sheeted branched cover of R2. Now, if you think of R2 as the complex Z-plane, then the cover is described by an equation, y squared equals z times z minus L, with branching at z equals 0 and L. To make an interval of length L, I've chosen the branching to be at z equals 0 and L. And then this simple equation, well, it has two values of y for each value of z, so it describes a double cover of the z-plane. Generically, there are two distinct values of y. They become equal at z equals 0 and L, where we have branching. And this Riemann surface is a two-sheeted cover of the z-plane with branching at the two endpoints. So what we're supposed to have learned from this analysis is that trace rho squared is a path integral on a double cover of the plane. Now, if we want to trace rho to the n, it would be similar. We would then have a bunch of copies of rho each represented by path integrals on cut planes. And then to get trace rho to the n, we would glue the upper part of the cut on one sheet to the lower one on the next. And then we'd keep doing that. And with some mental gymnastics, you would see that we would have constructed an n-sheeted cover of the plane branched over the 2.0 and L and describable by a slightly more general equation. So the path integral on this n-sheeted cover computes the trace of rho to the n. Any questions on that? Okay, well, there's a more convenient way to do it, though. the more convenient way to do it is to take n copies of the original CFT. By the way, everything I've said until now really wasn't special to two dimensions. A similar derivation in any dimension would tell us that trace rho to the n can be computed by a path integral on an n-sheeted cover of the original spacetime branched over the boundary of the entangling region. However, instead of the path integral and the n-sheeted copy, we will, however, now start saying things that are much simpler in two dimensions. Instead of an n-sheeted cover of the original spacetime, we take n copies of the original conformal field theory on one copy of spacetime. So we just say that we're on R2, and instead of saying that spacetime has n sheets, we say that on a single spacetime, there are n copies of the original theory. But then we introduce a twist field theta in this CFT that permutes the n copies. So what that means is that if you have a point in R2 where the field theta is, operator theta is inserted, that if you go around that point, the n copies are cyclically permuted. So any operator in, for example, the second copy, if it is transported around theta, will come back to an equivalent operator in the third copy, and so on. So the adjoint operator, theta dagger, permutes the n copies in the opposite direction. So now you see the path integral. So the path integral of a single theory, the original CFT, on the space-time that was an nth copy, is the same as the 2-point function of theta in one copy. Well, that's kind of a fancy, you'll see it's useful in a second, but it's kind of a fancy tautology. Sorry, not in one copy, in n copies. A single sheet in the n copy theory is equivalent to n sheets in the one copy theory. And the twist operator means by definition that the copies are cyclically permuted when we go around these points. So if we were doing a path integral, we would have n fields 5x1 up to 5xn, except that going around the twist field would permute 5xk to 5xk plus 1 when we go around theta. And that's exactly what happens geometrically when we had the n-sheeted spacetime with the n-sheets that are cyclically permuted. That simply produces the cyclic permutation that's needed to compute trace of rho to the n. So our problem is reduced to a 2-point function in a CFT. Now, a 2-point function, and here's where we really will use conformal invariance. This is the first place we really use conformal invariance. A 2-point function depends only on the dimension delta of the operator theta. Up to a multiplicative constant. So conformally invariance implies that theta of 0 times theta dagger of L can only be L to the minus delta. Oh, sorry, minus 2 delta because there are two operators. Up to a constant. Well, by dimensional analysis, the constant will have to be, make it L over epsilon to the minus 2 delta, and then there could be some other constant in front. So the general form of theta of 0, theta dagger of L, is L over epsilon to the minus 2 delta times a constant, if I assume that theta has dimension delta. That's pretty much the definition of saying that an operator has dimension delta. But the point is that in conformal field theory, it's natural, well, roughly speaking, all operators can be decomposed as sums of eigen operators of the dimension operator. But we're about to see that our theta does have a definite dimension delta. Now, in a moment, we'll compute that theta has dimension delta equals C over 12 times n minus 1 over n. C is called the central charge of the CFT. And n appears because theta is bringing about this cyclic permutation of n copies. So we'll compute that in a second. But when we compute it, then we'll have the trace of rho to the n. We learned that this is rho for the interval. That's theta of 0, theta dagger of L. That's a constant times L over epsilon to the minus 2 delta. So L over epsilon to the minus C over 6 times n minus 1 over n. And then we'll compute that it'll follow that S of the entropy just by differentiating this formula at n equals 1. We're going to learn so I want to be more careful. C was a constant for fixed n. I don't want to call it C because that is the same symbol we used for central charge. I'll call it W. So because I didn't say anything about how to normalize theta for different n, the so-called constant is really a function of n. So the general form of trace rho to the n is L over epsilon to the minus 2 delta times some unknown function of n. Then if you calculate the entropy from this formula, you'll get a constant minus W prime of 1 plus C over 3 times the logarithm of L over epsilon. So this bit will come by differentiating this thing with respect to n. And this will come by differentiating the normalization constant W of n. Now this is the interesting and universal UV divergence. And well, we'll see both the fact that it's divergent is important, but also the fact that it's proportional to C over 3 is important. We'll find that this formula has a lot of implications and applications. This constant is non-universal and uninteresting. It's clear that it must be non-universal because I didn't tell you exactly what ultraviolet cutoff to use. And different ultraviolet cutoffs will amount to using different epsilons in this formula. And so they will differ by shifts of this constant. So if you like, the really interesting part is the dependence on L. Then for dimensional reasons, it's L over epsilon plus a constant. But the constant depends on exactly how you defined epsilon. So to get this formula is a straightforward matter of differentiating this expression once we know that it's true that theta has this dimension. So that's the next thing I'll explain, but I want to stop here again for questions.
I have a question about the definition of the twist operator.
Yes.
When you defined it, you said that it, as you go around it, it permutes the copies of the CFT.
Yes.
I'm just not quite clear on what it means to sort of go around an operator insertion.
Locally, the path integral in the presence of theta is just n copies of the original path integral. You're integrating over fields. Well, you're integrating over n identical fields. And the action is a sum of phi k of x. The same action for each. But that's actually only a local description. Phi is not single valued. The phi's are not well defined at the positions of theta. And literally, if you go around, you come back to phi k of x after it makes a trip around theta, comes back as phi k plus 1 of x. Remember, what we're reproducing is a single copy of phi on the n-sheeted cover. On the n-sheeted cover, I think you would understand it without any question, right?
Yep.
The kth phi is the value of phi on the kth sheet. But you know that when you go around the branch point, you come back to the next sheet. So phi k just behaves like the original field phi on the kth sheet. It has the same property. Classically, you might say they're all equal at the branch point. But if you're away from the branch point and go around the circle, go around theta, you'll not come back to yourself. You'll come back to the next one of the series. It's somewhat the most elementary, well, historically, the original example of something of this kind was what's called the, unfortunately, I forgot what it's called, the disorder field in the Ising model. The twist field of the Ising model, which creates a cut in the Ising field so that the Ising spin, if it goes around the cut, comes back with the opposite sign. This is a generalization of that.
Thank you.
Sure. Any other questions?
But maybe just can you understand this like in a Hilbert space formalism, or it just seems to rely very much on thinking about it in terms of path and calls, but
Well, that's actually a good question. Let me finish the derivation and I'll try to go back to that. The answer is yes.
yeah, perfect. Yeah.
But sorry, I'll give you an abstract answer. So I'll tell you how to figure out what the answer is. I think your question is, how does the twist operator act as a Hilbert space operator?
Yeah, exactly.
So to answer such a question, you look at not theta, but theta times e to the minus epsilon h on each side for small epsilon. Then after answering the question for small epsilon, you take the limit as epsilon goes to 0. Now it's conceptually clear. Theta is in the middle of the sandwich. We have a wave function that depends on n fields below and it depends on n fields above. And we have the path integral recipe where we do the integral in the sandwich with the fields having a branching around theta. So by studying the picture, you would arrive at a Hilbert space interpretation of theta. But it's not that simple. It's much easier to understand in path integrals.
I see. Thanks.
I have a quick question. When you're studying open string amplitudes, there is a trick you can use that is to put image charges to solve the boundary conditions. Is there something similar here in the unsheeted version of R2?
I don't think so.
Okay, thanks.
Any other questions? But you can use conformal invariance. Okay. Given conformal invariance, you can compute a lot of things that would be hard to calculate in general. So this two-dimensional conformally invariant case ends up being much easier, simpler than other cases. But for our purposes, I just want to show, to justify this formula for the dimension of the operator theta. So we're going to use what's called the operator state correspondence. Of conformal field theory. So the idea is that here's the path integral in the plane, and here's a point where we're inserting some operator. Well, the plane, well, the operator creates a kind of singularity. If you were measuring some other operator, it would have a singularity near O. So generically, other fields are singular at O. Some other field would have a short distance singularity if you move it near O. And that suggests removing the point where the operator is inserted and using the fact that the punctured plane I can't write. The punctured plane is conformal to a cylinder. So by an elementary conformal mapping, there's a conformal mapping where 0, the position of the operator, goes to minus infinity. And infinity on the plane goes to infinity on the cylinder. So the operator lives at time minus infinity. Let's say there's Euclidean time running up. The time that runs up corresponds to the logarithm of the distance in the other picture. So in this operator state correspondence, an operator corresponds to a state psi sub O, a state on the cylinder. But the energy of the state is equal to delta minus C over 12, where delta is the dimension of the operator and C is the central charge. So for our purposes, this can be the definition of C, although I imagine a lot of you have studied some conformal field theory and are familiar with other definitions. This formula assumes that the circumference of the cylinder is 2 pi. Otherwise, so if the circumference of the cylinder is 2 pi L, I don't want to call it L because that's meant something. If it's 2 pi R, then we'd have an extra factor of 1 over R in the energies for dimensional reasons. So this formula, for our purposes, we can think of as the definition of C. And this one follows from this one, but one-dimensional grounds. Delta and C are dimensionless numbers, but energy has dimensions of 1 over length. So for general circumference, the energy is proportional to 1 over R. Now let's look at the case where L is the twist field in n copies of the original CFT. Well, we'll put the n copies on a circle of circumference 2 pi. I'm just drawing a single cylinder. I'm not going to try to draw n copies of it. But at time minus infinity, we have this operator theta, which permutes the n copies. The n copies are cyclically permuted. So it's like 1 copy on a circle of circumference 2 pi n in the original theory. So so the ground state energy in the presence of theta will compute in this description. So that means we use the original C and we can use delta equals 0. In the original theory, the circle has n times the circumference, but there's no operator inserted. Theta was just permuting the n copies, so when we go to the n-fold cover, there's no operator there anymore. It's like the identity operator with delta 0. And we can also use the original C, but we have to remember that the circumference is n times bigger. So we have to use this formula. So the energy is, well, it's delta, it's 1 over n times delta minus C over 12 minus C over 12n. So that was the computation in the original theory on a big circle. But we can also compute E in the n copy theory on small circle. Then there's no n. The 1 over n is replaced by 1, but delta has to be replaced by delta theta, and C has to be replaced by n times C, because the n copy theory has C, which is n times bigger. So the second computation says that the energy is 1 times delta theta minus n times C over 12. The first computation gave minus C over 12n. So combining these formulas, you learn that delta theta is C over 12 times n minus 1 over n, which was the formula that I claimed. So I'd hoped to discuss Rendler space today, but I guess we've run out of time, so we will have to leave that for Thursday. I'll just stop and ask for questions on this derivation.
I have a question. What would have happened if we have chosen not to state correspond to delta equals 0?
I think your question might be, what would happen if we studied the density matrix of a state other than the vacuum? I think that's the correct version of your question.
I see.
And if you don't think that's your question, you'll have to ask your question again.
I thought that there is some choice on the entangling surface, and that would correspond to the choice of twist field.
Actually, the choice of twist field would only go into this uninteresting constant C of n.
I see.
W of n, I called it here. From the point of view of statistical mechanics, I think maybe the best answer is as follows. If you had a cutoff, if you reformulate this computation as a limit of a cutoff calculation, then all possible twist fields would appear with different coefficients. But in the limit that you try to remove the cutoff, what will dominate will be the most relevant twist field. And the most relevant one is the one that we assumed.
I see, thanks. I have another question. Did you have to assume CL equals C right, or is it irrelevant?
Well, we did have to assume that. The way we used conformal invariance was too naive if we don't assume that. I'm not sure what else to say right now.
I guess your video got cut off. I didn't hear, sorry.
Okay. I don't want to give a quick answer to the question, what happens if C left is not equal to C right? The trouble, you don't really, many things become anomalous, as you know well.
Mm-hmm.
But I think for this computation, you might get away with it. I don't want to insist, though, without more careful thought.
Okay, thank you.
Any other questions?
Maybe one question. Can in principle the constant W prime of 1 depend on the IR cutoff, like on the ratio of the IR and the UV?
Well, it really had to do with the normalization of the twist field. There wasn't an IR cutoff in this problem, right? We worked on the infinite plane.
Yeah, I wondered if it can somehow be necessary in some situations. Yeah.
Well, I can't, nothing comes to mind to tell you.
Okay, yeah, thanks.
Any other questions? Okay, if there aren't any questions, then on Thursday, we'll have to begin with Rindler space since we ran out of time. And then we're going to be discussing some basics of information theory. In fact, while I was giving the lecture, I had some regrets to not have done that first, because when I started talking about entropy, I was a little bit uncomfortable at not having better motivated the definition of von Neumann entropy. But anyway, hopefully it was clear enough today. Anyway, I'll see you Thursday.